Hello students, welcome to the amazing platform of PW English. So my dear students, today we are going to start the lecture 6 of solutions chapter, my dear students. Till now we have discussed about Raoult's law. We have also discussed about the difference between an ideal solution, a non-ideal solution and much more. So what are we going to discuss today? First, my dear students, we will be discussing azeotropes and then we will be discussing about colligative properties. What are the different colligative properties and detailed discussion related to this topic. So I hope all of you are super excited, just as am I. So let's start the amazing session. So what are we going to cover? We are going to cover colligative properties. There are different number of colligative properties. The first is lowering of vapor pressure, and then we'll be discussing elevation and boiling point. Also, we are going to practice a lot of questions, PYQs, so that we'll gain a little confidence. Okay, so let's start. First, my dear students, let's discuss a little about azeotropes. It is a very small topic. We'll just cover it very soon. Okay, what are azeotropes? Okay, now for understanding the azeotropes, you need to understand that we have been discussing about solutions. So my dear students, let us consider that we have a solution of two volatile compounds. Okay, let us say that I have a solution of two volatile compounds A and B. Both of them are volatile. Okay, so now my dear students, what I did is I know that what are their boiling points. Okay, let's say its boiling point is somewhere 100 degrees Celsius and the boiling point of this is nearly 98 degrees Celsius. Okay, yeah, so in order if I ask you that you have to remove, you have to separate these two solutions. How can you separate these two solutions? And I'm giving you a hint as well. I'm giving you a hint that if you, what you do, you heat the solution up. Okay, you'll heat the solution up, right? Yeah, and you will try that one of the following solution, one of the solution gets evaporated first, right? Yeah, before taking this example, I should take this example. Okay, I'll take one more example. I have again components, let's say C and D. Now C has, let us say, 40 degrees Celsius of boiling point and D has, let's say, 100 degrees Celsius of boiling point. So now my dear students, if I ask you that you have to separate these two volatile solutions as well, components as well, what will you do? You'll start heating the solution, yeah? And now when you will start heating the solution, what will happen? The temperature will rise to 10 degrees Celsius, then 20, and then 30, and then 40 degrees Celsius. Once the temperature reaches 40 degrees Celsius, the C component will start to evaporate, right? Yes, it will evaporate, yes. Now, but D, which is in liquid form here, my dear students, it has a boiling point of 100 degrees Celsius. Until now, the temperature is 40 degrees Celsius. So I can say that D will not evaporate. Yes, you will have vapors of. You will have vapors of C. Yes, you can collect these vapors. And then later, what can you do? You can condense them What does condensing means? That you are actually, what you are doing, you're trying to liquefy it, right? Yeah. So you condense these vapors and you get your C component. You get your C component here. Okay, yes. So my dear students, this process where you have a solution of two components with different boiling points, wherein you can evaporate one component which has a lower boiling point and then collect it in another container and condense it there. This is the best way you can separate these two components. And this process is actually known as distillation. Now, my dear students, you know how to separate these two. If I ask you that, can you separate these two solutions by the distillation process? You will be like, ma'am, here if I see that there is not a much difference in the boiling points. One is 98 degrees Celsius, one is 100 degrees Celsius. So if we try to separate them, we cannot separate them completely by the fractional distillation process. This process is actually more clearly, it is known as fractional distillation. So we cannot separate with this solution with fractional distillation, but we can separate this solution with fractional distillation. Okay, yeah, I hope you've understood this part now. What I want to tell you is that what azeotropes are. My dear students, azeotropes are actually binary solutions, which means that it is a binary solution. It has two components and both of them are volatile. First thing is azeotropes are binary solutions. Second, my dear students, the solution is such that you cannot separate its components by fractional distillation process. That is, their boiling point are not of much difference. The two components boiling point are not very far away from each other, and that is the reason we cannot separate them by fractional distillation. Okay, so two things we know about azeotropes. There is one more thing which you need to understand. See, I have been telling you that if you have a container, let's say you have a solution here, you have a component A here, and you have a component B here, and you have component A in the vapor phase as well and B as well. Okay, so if I ask you about the mole fractions, you used to say that mole fraction of A in the liquid phase will be XA, mole fraction of B in the liquid phase would be XB. Right, and the mole fraction of A in the vapor phase would be YA, and the mole fraction of B in the vapor phase would be YB. But my dear students, since we are explaining you these two factors differently, this means that XA cannot be equal to YA. XA is not equal to YA. Okay, this is the condition that we generally assume, right? Yes, but in azeotropes, my dear students, azeotropes are such solutions. So azeotropes are such binary solutions where the components mole fraction in the liquid phase is actually equal to the mole fraction in the vapor phase. That is, in that particular case, XA is equal to XYA. Okay, I hope you got this point. So now we are going to define azeotropes. Azeotropes are binary solution of two volatile components. Okay, I hope this is clear. Yes. So binary solution of two volatile components. We can say that it cannot be separated by fractional distillation process. Fractional distillation process. Okay, I hope this is clear. Two conditions. First is binary solution of two volatile components. Second is that we cannot separate the components by the fractional distillation process. And the third is that the mole fraction of the components in the liquid phase is equal to the mole fraction in the vapor phase. Okay, so all these three combined actually define a azeotrope, a binary solution of two volatile components which cannot be separated by the fractional distillation process, and the mole fraction in the liquid phase is actually equal to the mole fraction in the vapor phase. These are what are known as azeotropes. You need not memorize all the azeotropes, my dear students. You only need to understand the examples, few examples which you need to understand. I'll give you the examples of azeotropes as well. And also, my dear students, you can actually differentiate the azeotropes in majorly two parts. And what are those two parts? One is the minimum boiling azeotrope and one is the maximum boiling azeotrope. Now we'll be understanding the difference between the two. Okay, yes. So now, my dear students, how are you going to understand that? For understanding that, you need to understand that, my dear students, I just told you that volatility is actually inversely proportional to the boiling point. Volatility is actually inversely proportional to the boiling point. The more volatile a component will be, the lesser will be its boiling point, and the more will be its vapor pressure. Right? Yes, I hope we are clear with this concept. Now, I have told you two non-ideal solutions, two types of non-ideal solutions, right? Yes, we talked about two two different types of non-ideal solutions. Right? Yes. What were these two? One was positive deviation from Raoult's law and one was negative deviation from Raoult's law. Now, I want to make you understand that the maximum boiling azeotrope and the minimum boiling azeotrope have a particular classification. Either they are positively deviated non-ideal solutions or they are negatively deviated non-ideal solutions. Now we are going to understand that concept. Okay. See, for a positive deviation, we know that according to the Raoult's law, whatever the pressure is calculated, the actual pressure is more than that expected, right? Yes. In positive deviation, the pressure obtained of the vapor pressure of the solution obtained is actually more than that expected from the Raoult's law. And in case of negative deviation, the vapor pressure is actually less than the expected vapor pressure of the Raoult's law. So now imagine, my dear students, in positive deviation, since the vapor pressure is more than expected, what will happen? Ma'am, the pressure will become equal to the atmospheric pressure more easily, means that the boiling point will reach faster. More the vapor pressure, lesser will be the boiling point. More the vapor pressure, so the boiling point will be less. So my dear students, let me tell you that your azeotropes are basically classified into two types. I hope you'll understand now. One is your minimum boiling azeotrope, one is your maximum boiling azeotrope. And the question that is generally asked to you is that the maximum boiling azeotropes are which type of non-ideal solutions, or the minimum boiling azeotropes are which type of non-ideal solutions. Now how you have to memorize it, I'm going to tell you that how you can understand the concept. Okay, see, minimum boiling azeotrope means that you can understand it, you can memorize it like this. Minimum boiling azeotrope means the azeotropes which will boil at a minimum boiling point, very less boiling point. If the boiling point is very less, this means that the vapor pressure would have been very more large. And if the vapor pressure is very large, this means that they might be which positively deviated non-ideal solutions. So my dear students, always and always here, these are positively deviated, I can say that positive deviation from our Raoult's law. Okay, positive deviation from Raoult's law. Okay, I hope this is clear with you. No issues. Now let's come to the maximum boiling azeotrope. If you found this, you can very easily find this. If you have maximum boiling azeotropes, this means that these azeotropes have very high boiling points. If they have high boiling points, this means that if they have high boiling points, this means that their vapor pressure should have been less. If their vapor pressure is less, this means that vapor pressure is less in case of negatively deviated non-ideal solution. So we can say that these are negative deviation from Raoult's law. So this is how you can understand this, that always and always, my dear students, a minimum boiling azeotrope will show a positive deviation from Raoult's law, and always a maximum boiling azeotrope will show a negative deviation from the Raoult's law. This is how you understand this part. Okay, yes, example is something which you need to learn, my dear students. So yes, these are the examples, and only this specific concentration is achieved, only this specific composition when achieved, they are known as azeotropes. Not in all concentrations. See, the concentration is given here. See, the concentrations are given here. That is the most important thing, that at this particular composition, it behaves like a azeotrope, right? Yes. So I hope this is clear with you. If you want to write it, you can write it, and then we'll move forward. Then this, my dear students, and then this. I hope you've written it. Now let's move forward. Now we are going to study about colligative properties. What are colligative properties? Can I have water? Then we'll move forward. Okay. So till now you can understand that what are colligative properties. The colligative properties are actually the properties which depend upon amount. Okay. So what are colligative properties? The colligative properties are the properties which depend upon the amount and not on the nature of your solute. Okay, or solvent as well. It could be solute or solvent, but we'll be discussing majorly the colligative properties which are depends on solute. Okay, so what are colligative properties? These are the properties which depend upon amount of substance. Amount of substance. Now let's understand what does it mean by amount of substance. My dear students, whenever in chemistry amount of substance is mentioned, this means that they are talking about moles. They are talking about the moles of that particular component. So colligative properties are those properties which depend upon amount and not on the nature. They do not depend on nature, which type of component it is. No, they don't care about it as long as the moles are equal. As long as the moles are equal. If there are two different components, they don't care as well as long as the moles of both of them are equal. These are known as the colligative properties. So colligative properties are the properties which actually depend upon the amount of substance and not on the nature of the substance. You can write it and not on nature of substance. Now we need to understand that what are the different types of colligative properties we will be discussing in this particular chapter. The colligative properties which we will be discussing here are the colligative properties which we will be discussing here, the first and the most important is lowering of vapor pressure. The first is lowering of vapor pressure. Okay, I'll write it here only. Lowering of vapor pressure. The second colligative property which we will be discussing is elevation of boiling point. Elevation in boiling point. Elevation in boiling point. The third colligative property which we will be discussing is depression in freezing point. Depression in, don't worry, we'll be studying each and every one of this individually, so you'll understand every part. You just need to write it right now, okay? And the last is your osmotic pressure. And the last is your osmotic pressure. So these are the colligative properties which we will be discussing in this particular chapter. Okay, yes, we'll be discussing one by one each, so don't worry. The first is lowering of vapor pressure, then there is elevation in boiling point, then there is depression in freezing point, and the last is the osmotic pressure. If you want to write, you can write, and then we'll move forward. Okay, now let's talk about lowering in vapor pressure. What is lowering in vapor pressure? See, my dear students, we have discussed this 100 lots of times, so you need not to be frightened by it. Actually, what happens is you have to consider two things. You have to consider two things, that you have a container and you have another container. Okay. Now, my dear students, what I want to tell you is that in this particular container, let us say you have pure solvent. You have pure solvent, and let us say that the vapor pressure of this pure solvent is P0. Okay. If you talk about this container, what we did, you had this pure solvent, and what you did, you added some non-volatile solute to it. So what did you do? You added non-volatile solute to it. So you added a non-volatile solute to this container. Okay. So now it is a solution. So now it is a solution, and let us say the vapor pressure of the solution is PS. Let us say the vapor pressure of this solution is now PS. Initially, you had a pure solvent whose vapor pressure was P naught, and then you had a solution whose vapor pressure came out to be PS. Okay. Now my dear students, if according to the Raoult's law, we calculate the vapor pressure of the solution, how are we going to calculate? According to the Raoult's law, we know that PS is equal to, you have two components here, you have a solute and you have a solvent, right? Yes. So PS will be equal to vapor pressure of solute plus vapor pressure of your solvent. Okay. Let me say that here P is the partial vapor pressure of solute. Also, since solute is a non-volatile solute, we also know that P is equal to 0. And P sol is the partial vapor pressure of solvent. Okay. Yes. So now my dear students, I can say that PS will be equal to, okay, I have written both of them PS. So let's say PS, P dash. Okay. So here P dash will be equal to 0 since the solid, your solute is a non-volatile solute. So it will not have any vapor pressure. So ma'am, PS will be equal to PS dash. Okay, it is P dash. I'm sorry. I'll just make it right. P dash. Okay. So according to Raoult's law, we can say that P dash into mole fraction of solute plus P sol, P naught into mole fraction of solvent, because I told you that P naught is the vapor pressure of your pure solvent. So if you want to write, you can write P naught is the vapor pressure of pure solvent. Okay. I hope this is clear. Now my dear students, I know that P dash is equal to 0. So PS came out to be P naught into mole fraction of solvent. This is the first thing that I came to know. Okay. So this is what we calculated first of all. Perfect. We don't have any issue till here because we have done this thing previously also. Also my dear students, you know that we know that PS is actually less than P naught. You know that the vapor pressure of the solution is less than the pure solvent's vapor pressure. We studied that as well. So if I ask you how much is it less, that will be known as lowering of vapor pressure, right? So let us say, let delta P is equal to lowering of vapor pressure. How much vapor pressure is lowered, that is denoted by delta P. So we can say that delta P is actually equal to what is the maximum value, which was initial P naught minus the PS. This much of the vapor pressure has been lowered, and that is known as the lowering of vapor pressure. So lowering of vapor pressure is given by delta P is equal to P naught minus PS. Delta P is equal to P naught minus PS. Okay. I hope it is clear to you. Now my dear students, let's use this equation, which lowering of vapor pressure we just calculated. We'll be using this. Delta P, which is your lowering of vapor pressure, is actually equal to P naught minus PS. You just calculated PS value. This is your first equation. So you just calculated the value of PS, just put it into that equation. So put using 1. We can say that delta P is equal to P naught minus, what is the value? P naught into mole fraction of solvent. So P naught into mole fraction of solvent. Okay. I used the first equation in this. So what did I get? I'll take P naught common. This will be 1 minus mole fraction of solvent. I know that the solution was binary. Since solution is binary, we know we know that mole fraction of solute plus mole fraction of solvent is equal to 1. So 1 minus mole fraction of solvent will be equal to mole fraction of solute. I hope this is clear to you. Yes, ma'am. So we are using this in 2. So using in 2, we can say that delta P is equal to P naught into mole fraction of solute. Delta P is equal to P naught into mole fraction of solute. This is the required expression. This is the required expression for your lowering of vapor pressure. So this is the required expression for lowering of vapor pressure. Now I want to show you that how lowering of vapor pressure is a colligative property. You know that P naught is the vapor pressure of pure solvent. Yes, ma'am. And it is a constant value. P naught is a constant value, hai na? So we can say that P naught is constant. So my dear students, can we say that delta P is directly proportional to the mole fraction of solute? Yes, ma'am. The more the mole fraction of solute, the more will be the lowering in vapor pressure. The more there will be the non-volatile solute, the more will be lowering of the vapor pressure. And this you can understand conceptually as well, that you had this container, and the more you will add the non-volatile solute to it, the more surface particles, the surface will be covered by your non-volatile solute, and the lesser vapors will be formed, and eventually there will be less of the vapor pressure for the solution, right? Yes. So we can say that lowering of vapor pressure is actually a colligative property with respect to the solute, right? Yes. So here you can say that lowering of vapor pressure is a colligative property, with respect to the solute. I hope this is clear to you. I hope this is very clear to you. There is no issue with this. Perfect. Very good, my dear students. So this is how you calculate the lowering of vapor pressure. Okay. If you want, you can write this. What did we do? We first calculated the vapor pressure of the solution. The solution's vapor pressure, according to Raoult's law, should be equal to PS is equal to P naught into mole fraction of solvent. Then we calculated the lowering of vapor pressure. How much vapor pressure will be lowered? P naught minus the solution's vapor pressure. We added the value of PS, which we calculated here. We know that 1 minus mole fraction of solvent is equal to mole fraction of solute. We used it and we got the expression. Okay, so for me, my dear students, needs to only and only understand this expression. You can calculate anything, but if you want to memorize the formula, I'll help you with that as well. Now, using this formula, using this particular formula, delta P is equal to P naught mole fraction of solute can also be written as delta P is equal to P naught moles of solute upon moles of solute plus moles of solvent. Okay, so if you want, you can use this formula as well. You can use this formula as well. Or else, my dear students, there is a condition, you can write it as note for very dilute solutions, what happens, my dear students? Moles of your solvent are very much more than the moles of solute. Generally, when we talk about solution, we talk about dilute solutions. And whenever you have dilute solutions, then you know that moles of solvent are much more than moles of solute. So when you add moles of solute plus moles of solvent, you can actually ignore the value and you can say it is equal to moles of solvent. So the above expression becomes delta P is equal to P naught moles of solute upon moles of solvent. So This is the required expression when you are given that your solution is very dilute. Then what can you say? You can say that the moles of solvent were much more than solute, so the addition of these two will be nearly equal to the moles of solvent. Okay, so this is how you can express lowering of vapor pressure in different formulas, but if you know one formula, you can calculate n number of formulas yourself, right? Yes, I hope this is clear with you. If you want to write, you can write it, my dear students. Let's move forward. I hope you've written this. Perfect. Now, after this, what are we going to do? Now, my dear students, we have discussed about lowering of vapor pressure. Now we are going to discuss one little more thing, which is relative lowering of vapor pressure. Okay, it is also not complicated. It is very easy, my dear students. It is relative lowering of vapor pressure. So the heading would be relative lowering of vapor pressure. So how do we calculate the relative lowering of vapor pressure? For that, we only need to understand the formula which we have still calculated, lowering of vapor pressure. We'll start from there. We know that delta P is equal to P naught mole fraction of solute, right? We know this. What are you going to do? Just do this, that you bring this P naught below here. This will be equal to mole fraction of solute. Okay, so now, my dear students, what I want to tell you is this is the required expression for relative lowering of vapor pressure. So what is the difference between lowering and relative lowering? For lowering, delta P is denoted as lowering of vapor pressure, and if you talk about relative lowering, then you bring the P naught down here, and that whole term is actually known as the relative lowering of vapor pressure. Okay, yes, I know that we know delta P is equal to P naught minus P S. So use this in this particular part. This will be equal to P naught. This will be equal to P naught minus PS upon P naught will be equal to mole fraction of solute. So this is an expression which you can memorize or don't memorize. It is also okay, because you understand the concept. That is the most important thing. Okay. So this is the relative lowering of vapor pressure. Okay, also you can just open it and write in n number of ways, my dear students. You can write it as P naught minus PS upon P naught is equal to moles of solute upon moles of solute plus moles of solvent. Okay, and if you have a very dilute solution, what can you say? Let's write it for very dilute solutions. For very dilute solutions, I know that moles of solvent are much more than moles of solute, right? Yes, so we can write the expression as P naught minus PS upon P naught will be equal to moles of solute upon moles of solvent. So this is the expression that you can use for the relative lowering when you are given very dilute solutions. So in every formula which you studied for lowering, just what you are supposed to do, bring that part, P naught part below. That will be your lowering expression. So this whole complete thing is known as the relative lowering of vapor pressure, right? Yes, so you are asked a lot of questions based on this, that calculate the lowering of vapor pressure, calculate the relative lowering of vapor pressure. Then you have to solve the questions accordingly what is asked in the question. I hope it is very clear to you. You can just understand it, you can write it, and then we'll move forward. I hope you've written it. You can write this, my dear students. Okay, perfect. So this was all about lowering of vapor pressure and relative lowering of vapor pressure. We'll be solving questions based on this, don't worry, in the end. Okay, we'll be discussing. Let me see if we have any question, direct question related to this. We have the boiling point question. The vapor pressure of benzene at a certain temperature is 640. A non-volatile electrolyte weighing this gram is added to benzene. The vapor pressure of the solution is 600. What is the molecular weight of the solid substance? Okay, try to do this question, my dear students. Try to do this question. Pause the video and try this question, and then we'll solve this question ourselves. Okay, I hope you've tried this. It is a previous year question. Now ma'am will be solving this question with you. The vapor pressure of benzene at a certain temperature is 640 mm. So my dear students, you have been given the vapor pressure of benzene as 640 mm. Just a second. The vapor pressure of the solution is, okay, you are given this vapor pressure of solution as 600 mm of Hg. You are given the pure vapor pressure P naught for benzene as 640 mm of Hg. What else you are given? You are given a non-volatile and non-electrolyte solid weighing 2.175 grams. So your mass of solute is given to be how much? 2.175 grams. Okay, is added to 39.08 grams of benzene. And you have benzene, my dear students, and mass of benzene is given to be how much? 39.08 grams. See what, and you are supposed to calculate the molar mass of solute. So this is the question, and you have to solve this question. Try this question, my dear students. I hope you can do this question yourself, and then we'll move forward. Okay. So अब अगर आपने ये question try किया होगा तो you would have understood, my dear students, here that everything is given here. What you have to do is only and only you needed the molar mass of benzene here, and you needed the correct expression, and you could have calculated it very easily. Okay, so now if we write the expression for lowering of vapor pressure, it is delta P is equal to P naught mole fraction of solute. Mole fraction of solute, right? Yes. So now delta P is equal to, ma'am, delta P is equal to P naught minus PS upon P naught, right? Yes. And this will be equal to mole fraction of solute. What will be the mole fraction of solute? Moles of solute upon moles of solvent. So now, my dear students, what I have assumed on my own is that I have assumed that it is a dilute solution. Try to solve with this expression because your options are very far away from each other. So the closest answer would be your correct option. Always try to solve the question with the trick. Okay. So I considered it a dilute solution because the answers were not very close to each other. They were very far away from each other. So I could have assumed this to be like this. Okay, now try to solve it. You have P naught value equal to 640, then you have PS value equal to 600 divided by 640. This will be equal to moles of solute. You have given mass of solute, but you don't have molar mass of solute, and that is what you have to calculate. So 2.175 upon molar mass of solute, which we are supposed to calculate, divided by moles of solvent. Your solvent is benzene. Benzene's mass is given 39.08 divided by molar mass of benzene. My dear students, the molar mass of benzene is 78 grams per mole, which you need to know. 78 grams per mole. Benzene is C6H6, my dear students, and you can calculate the molar mass of this. Okay, yes. So now if you see that you have everything, you only have one variable to calculate, and you can calculate it from this particular equation. Okay, so just calculate and pick the correct answer. I hope you're clear with this concept. So this is how you will find numericals related to lowering of the vapor pressure. Easy? Yes, you just need to understand what is asked in the question. Now, my dear students, let's move forward now to the another colligative property, which is elevation in boiling point. Now we are going to understand elevation in boiling point. Just a second, just let me check one thing. That is it getting recorded? Yeah, it is getting recorded. Perfect. Okay. Sometimes what happens now, I start recording the class. I mean, I assume that my recording is started, and I start teaching, and after 15 minutes or 20 minutes I realize that I haven't clicked the recording button. So this is what happens sometimes with ma'am, so ma'am has to cross check. Okay. Okay, now let's start with elevation and boiling point. What actually happens in elevation and boiling point is you'll understand this very easily, because I have made you clear with the vapor pressure concept. Okay, now my dear students, again you have to consider two containers. Okay, you have one container here and you have another container here. Now let us say this is your pure solvent, and let us say this is your solution. Okay, now I know that pure solvents vapor pressure, is given by P naught, and the solution's vapor pressure is given by PS. Now since we are talking about the boiling point, so I am myself giving here the expression TB naught. This is the boiling point of pure solvent, and TB is the boiling point of your solution. So you can write here as TB naught is the boiling point of pure solvent, and TB is the boiling point of solution. Okay, so you have the boiling point of pure solvent and you have the boiling point of your solution. See, till now whenever I used to tell you about the vapor pressure, I used to ask you one question only. What was that question? The question used to be, can you tell me which of the following is larger? Right? Yes, which of the following is more? Now I want to ask you the same question again. Out of TB and TB naught, which is higher? Out of TB and TB naught, which is higher? You have to answer me. Very easy, right? Yes, you can answer me. You only have to use this. Only this. Let's start. Okay. I know. I have I think discussed this n number of times, that out of vapor pressure of the pure solvent and vapor pressure of the solution, the vapor pressure of the pure solvent is more. Okay, yes. Now we also know that more the vapor pressure, more the volatile your component is. Volatile, spelling is wrong. Volatile. More will be the vapor pressure and lesser will be the boiling point. This is something we have been discussing a lot of times. Okay, now see, you have more of the vapor pressure. Now imagine you have this solution, pure solvent, and you have solution, and you started heating both of them. What will happen? Ma'am, this pure solvent will form more vapor as compared to this solution. Since it will form more vapors, there is a possibility, or it will definitely happen, that at a lower temperature, this solution solvent will actually have vapor pressure equal to the atmospheric pressure, and that will be its boiling point. This means that, ma'am, more the vapor pressure, lesser will be the boiling point. Since pure solvent has more vapor pressure, the boiling point of pure solvent will definitely be lesser. So you can say that TB naught will be lesser than TB. TB naught will be lesser than TB. You can explain this in your words. That more the vapor formed, lesser will be the boiling point. I hope this is clear with you. More the vapors will be formed, lesser will be its boiling point, and that is the reason that boiling point of solution is higher than the boiling point of pure solvent. Clear? I think this is clear. I don't think there is any issue till now. Yes? Yes. And that is the reason. That is the reason. First, you had some boiling point TB naught. Then you added a non-volatile solute. Then you added a non-volatile solute to it. And what happened? The boiling point raised. And that is the reason we say it is elevation in boiling point. Initially, what happened? You had a vapor pressure. The vapor pressure of the solution decreased. So that was lowering of vapor pressure. And since here boiling point is increased, so we say elevation in boiling point. Okay, I hope this is clear with you. Very good. Now, my dear students, now if I ask you that let us say delta TB is actually the difference between, this is actually the elevation in boiling point, how much elevation has taken place. So let delta TB is elevation in boiling point. So delta TB is the elevation in boiling point. Also, I know that delta TB will be equal to TB minus TB naught. Why? Because TB is greater. So TB minus TB naught will be equal to the elevation in boiling point. Now, my dear students, I want to ask you same as in lowering of vapor pressure, the more the non-volatile solute we were adding, the more the difference was in the vapor pressures of the two solutions, pure solvent and solution. Same way, the more I will add the solute, the more will be the concentration of that solution, and that's the more will be the concentration of the solution, and the more will be the lowering of vapor pressure, and ma'am, the more will be the difference in the boiling points, right? Yes. So this means that elevation in boiling point is also a colligative property, which only and only depends on the amount of your non-volatile solute added to it, because the amount of non-volatile solute, more the amount of non-volatile solute you add, the more will be the concentration. And scientists with n number of experiments finally calculated. First, you have to write this. First, write this. Elevation in boiling point is a colligative property. I hope we've understood this, that why it is a colligative property. Yes, we've understood this. Why is it a colligative property? Now I want to tell you, the more the amount concentration of the solution, the more will be the difference in the boiling points. And that is the reason it is said that delta TB, that is your elevation in boiling point, that is the difference in the boiling points, will be directly proportional to the molality of the solution. It will be directly proportional to the molality of the solution. Now you will have a question that, ma'am, why only molality, my dear students? Because with calculations, this was the concentration term which was giving you the best results, and that is the reason the scientists use molality. Okay, there is no another explanation to it. It is the concentration term which scientists finally decided to give in the formula, so you will have to accept it. I can't help you with that. Okay, so just deal with it. So delta TB is directly proportional to molality of the solution. So I can say that what is M of SOL? This is the molality of solution. Okay, I think this is clear with you. Now, my dear students, when we remove this proportionality, then delta TB comes out to be KB into molality of the solution. Now, what is this? What is this KB, my dear students? It has a very important role to play. There are a lot of questions that are asked from this part, my dear students. KB is actually known as the ebullioscopic constant. KB is actually known as the my spelling could be wrong, just check it, ebullioscopic constant. Okay, or it is also known as molar elevation constant. It is also known as molar elevation constant. These are the names with which it is known. And also, my dear students, Kb is a constant which only and only depends on the nature of your solvent. Different solvents will have different Kb values. So this is the first thing which you need to understand. The second thing which you need to understand is that Kb, different solvents have different Kb values. We can also say that Kb depends on the nature of the solvent. Okay, yes. So these are the things which you need to understand. The next thing which you need, okay, first you have to understand this part. I hope you've understood it. So if you want to write it, you can write and then we'll move forward. I hope you've written it. Now I hope you've written this as well. Okay. Now we are going to talk about a little about the unit of your ebullioscopic constant. So now we are going to talk about units of Kb. So now, my dear students, what is the unit of Kb? I know that delta Tb is equal to Kb into m. Right? So what will Kb be equal to? Kb will be equal to delta Tb upon m. Right? Yes. Now, what can be the unit of Kb? Since, my dear students, it is the difference of temperature and we take temperature in Kelvin, ma'am, the unit here will be Kelvin. Divided by, ma'am, down in the denominator we have molality and the unit of molality is mole per kg. So from here we can say that unit of Kb came out to be Kelvin kg per mole. Kelvin kg per mole. This is the unit of Kb. Okay. Now, I told you that different solvents will have different Kb values. So you need to understand that as well, that different solvents will have different Kb values, but you will be given in the question the values as well. For example, Kb value for water is 0.52 Kelvin kg per mole. This is the example, same as water. Different solvents, for example benzene or ethanol, any solvent will have its Kb value and it will be given to you in the question. Don't worry. Okay, so this is the thing which you need to understand about Kb. Okay, yes, I hope you're clear with this. I hope you're clear how the elevation in boiling point comes out, how it depends, how can we classify it as a colligative property. I hope you understood the expression, how to calculate the expression, and I hope you understood that what is Kb and how, on what things does it depend and what is the unit of Kb. These are some questions which are asked to you. Okay, clear. Now the next thing that we are going to discuss is the graph. Now we are going to discuss the graph. So in graph, I want to ask you some question, and that question is actually asked in JEE as well. So with graph understanding, we'll also learn how we'll solve the JEE questions. Okay, so JEE question in, I don't remember the year, but yes, this question was asked and it is a very good question. Okay, it is a straight line. Okay, now what I did is that let's say on this part you have the vapor pressure, and let's say at this part you have the temperatures, at this part you have the temperature, or better to say you have the boiling points, let's say Tb. Okay, now I am giving you two curves. You have one curve here, you have one curve this, and you have the other curve this. Okay, yes. So my dear students, my question to you is out of these two, one is for solvent, pure solvent, and one is for solution. So you have to to tell me, just by seeing this graph, you have to tell me which line is your pure solvent and which line is your solution. Pause the video, try yourself. It is the most amazing part. Pause the video and try it yourself. Okay. I hope you've paused the video. I hope you've tried this question, because now I'm going to tell you this in two different ways you can calculate this. Very easy, my dear students. Imagine what happened is let's say we took two solutions. We took a pure solvent and we took a solution as well, and we fixed one particular temperature. We fixed one particular temperature. Okay. If I fix, I'll say it as temperature. Now see. Now it is better if I'm sorry. Now, if you fix the temperature, let's say I started I started heating my pure solvent and my solution at a one particular temperature, and I thought that at a particular fixed temperature, let us say 50 degrees Celsius, I'll stop heating both of them. The one which will have more vapor pressure obviously will be my pure solvent, and the one which will have lesser vapor pressure will be my solution, because I know that for a pure solvent, vapor pressure is more at a particular temperature as compared to the solution, right? Yes. So the first possibility is I have to fix the temperature. Okay. Yes. So let's fix the temperature. So in this particular case, what you did, you fixed the temperature. So this is the temperature. So this is the temperature I want to fix. Okay. I want to make a straight line, so I'll make a straight line. So I fixed the temperature and I made a straight line. Okay. Now, I still don't know which is solvent, which is solute, but I know that the vapor pressure of the solution is always less than the vapor pressure of the pure solvent. Okay. So the pressure corresponding to this particular line is this, let us say P1, and the vapor pressure corresponding to this line is P2, and I know that here P2 is more than P1, here P2 is more than P1, and I know that the vapor pressure of the pure solvent is always more, so P2 should be a solvent, right? Yes. So this, I can say that this will be P2 and this will be P1, which tells me that the first curve is actually for pure solvent and the next curve is actually for solution. This is for solution. This is how you actually calculate, you find out which is your pure solvent and which is your solution. Okay, let's talk about the other possibility. What can you do? See, if I fix a pressure, see, I have fixed a pressure, particular amount of pressure, that if, let us say 60 mm of Hg vapor pressure comes out, this is my maximum pressure. I know that corresponding to that I will get temperatures which I can say that they are their boiling points. Let us say atmospheric pressure. If you consider atmospheric pressure 1 atmosphere, so now you are trying that both of them comes at atmospheric pressure. You know that boiling point of your solution is always more than the boiling point of your solvent, pure solvent, right? You know this, that the boiling point of your solution is always more than the boiling point of your solvent, right? Yes. I hope this is clear with you. Yes, ma'am. So now, my dear students, so now what will I do? I'll fix the vapor pressure. So let's fix the vapor pressure now. I'll use this color. I have fixed the vapor pressure now. So the temperature corresponding to this is this, okay, and this will be T1, and the temperature corresponding to this is T2, okay. Yes, I think this is clear. I know that T2 is more than T1, right? Yes. So this means that this is T2 and this is T1. This means that This means that the temperature, this line actually is for solution and this line is actually for pure solvent. You actually calculated both the things very smartly, right? Yes. So you can calculate from x-axis or y-axis, fix the temperature, fix the pressure. You can find out which is pure solvent and which is solution. Very easy, right? Yes. What I want to tell you is the graph here, my dear students. Let us say this was your solvent, pure solvent, and this is your solution. Okay. So now, my dear students, you know that the atmospheric pressure is 1 atmosphere. So you will fix the pressure. So the temperature corresponding to this particular part will be this will be actually TB, not because this is corresponding to the boiling point for the pure solvent, and the temperature corresponding to this will be TB. And if you see from graph as well, you can say that TB is actually more than TB not, and this particular part is actually known as your delta TB. This is actually known as your delta TB. So this is how you calculate or you understand the graph. Graph is very important, my dear students. You need to understand each and every part of your graph. I hope it is clear. You can make all the 3 graphs and then we'll move forward. The graphs are similar. You just need to understand it. And then this. Perfect. So let me tell you, the topics are complete. Now only and only we have to practice the questions. So it's very easy. If you understand the chemistry part, you will never need to memorize it. It is super easy, super interesting. Just you have to develop a little interest into it. You know, you should be curious about the things, that how can we calculate this, what is this happening, and all that you need to understand. Only then you can solve the questions as well. Okay, and you will understand the concepts and you're pro in physical chemistry. So now let's start and solve a few questions. So you have a question out here. What does the question say? You have 0.15 grams of solute dissolved in 15 grams of solvent. So the mass of solute is given to be 0.15 grams. The mass of solvent is given to be 15 grams. Is boiled at a temperature higher by 0.21 degrees Celsius, 216 degrees Celsius. This time, my dear students, if they are saying that it is temperature higher by, this means that they are actually telling you that delta TB is equal to 0.216. So you need to just understand that what are they trying to tell you. They are trying to tell you that delta TB value is 0.216. Okay. Then that of the pure solvent, the molecular weight of the substance is molar elevation constant, my dear students. Your Kb value is given to be 2.16. Okay, so I know that delta Tb is equal to Kb into molality. Okay, so delta Tb is equal to 0.216 is equal to 2.16 into molality. What is molality? Moles of solute upon mass of solvent in kg. So moles of solute 0.15 divided by molar mass of solute, which we need to calculate, divided by mass of solvent in kg. So I'll have to divide it by 1000. If you see, you have everything given here. You only need to calculate molar mass of solute, and that is what is asked in you in the question, the molecular weight of the substance. So I hope you have an equation. You can calculate the molar mass of the solute from this particular part. Such an easy question, you see. Such an easy question. So you only have to solve these types of questions. Okay, just take the correct answer out of these and then you're good to go. Okay, yes, perfect. Let's move forward and do the next question. Next questions on your screen is here. This is a little bit trickier question, but you need to do this question. Only then you will see how tricky questions can be asked. It is also a NEET question, my dear students. Okay, the question says that at 100 degrees Celsius, the vapor pressure of a solution of 6.5 grams of solute. So the first important thing, that mass of solute is given 6.5 grams of a solute in 100 grams of water. So the mass of solvent, that is your water, is given to be 100 grams. Okay, is 732 mm. Okay, the vapor pressure of solution. You have been given the vapor pressure of solution, which means that you have been given PS equal to 732 mm of Hg. Yes. Now, my dear students, you are given the Kb value as well. You are given the Kb value as well, which is equal to 0.52. Okay, you have to calculate the boiling point of this solution. You have to calculate the boiling point of the solution. Now, there are a few things which you need to know here, my dear students. Since they are talking about the vapor pressure, my dear students, then you have to understand the vapor pressure of pure water is actually 760 mm of Hg. This is something which you need to know. Sometimes in question this will not be given, but you need to know this particular part, that the vapor pressure of pure water, the vapor pressure of pure water is 760 mm of Hg. Okay, now you have all these things. And you have to calculate the boiling point. You have to calculate the boiling point. Now, my dear students, one more thing you need to understand, that boiling point of pure water is, I hope everybody knows this, 100 degrees Celsius, which is 273 plus 100, which is 373 Kelvin. Okay, so these are the two things which you were supposed to know yourself, because it is not given in question. Now, how you're going to do this question? If I see here something related to vapor is given, but something asked related to boiling point, how are we going to connect both of them? Okay, they have asked me the boiling point of the solution. I know that delta TB, which is equal to TB minus TB naught, is equal to KB into molality, right? Yes, I know this. Okay, for this I know that TB is to be calculated, because they have asked you the boiling point of the solution. So that is something which you have to calculate. TB naught we just calculated, my dear students. It is 373. This is equal to KB value you are given. It is 0.52 into, my dear students, molality, which means moles of solute upon molar mass of solvent in kg. Mass of solvent in kg. You have been given the mass of your solute 6.5 grams. Divided by molar mass is not given, but mass of solvent is given, which is 100, and I need that mass in kg, so I'll divide it by 1000. So this is the expression, but to calculate this expression, to calculate TB, I need to know the molar mass of the solute. I don't know what is the molar mass of the solute. So to calculate the molar mass of the solute, you need these values. Now is the best part coming here. You know that lowering of vapor pressure, delta P is equal to P naught into mole fraction of solute. We are again considering it a dilute solution. So P naught minus PS upon P naught is equal to moles of solute upon moles of solvent. Okay, now you have P naught value equal to, 760 minus PS is given to you, which is equal to 732. So this will be 732 upon 760. This will be equal to moles of solute. Moles of solute will be given mass of solute, which is 6.5 divided by molar mass of solute divided by mass of solvent. Solvent is water. So given mass of solvent upon molar mass of water is 18 grams per mole. So from this equation, you can calculate molar mass. I hope you can calculate molar mass. Yes. Calculate the molar mass here. Use this in this particular expression. Okay. Let us say this is your first equation. So you will have to use this molar mass value in 1. And you can calculate the TB value. So this is something very unique, where you have used both the expressions to calculate one particular part. Okay, so this is a very important question. I'll make you understand this again, my dear students. You were given the vapor pressure of water. Now, no, you were given the vapor pressure of the solution. You need to know that the vapor pressure of the pure water is 760 mm of Hg. So I have marked it. This is something you need to know yourself. You also need to know that the boiling point of water is 100 degrees Celsius, and you always use the temperature in Kelvin. So you will convert it into Kelvin. Then you will use the expression delta TB is equal to KB into M. You'll write TB in minus 373, you calculated it. 0.52 was given, mass was given, molar mass you had to calculate, and mass of solvent was given, so you calculated the molality. Now, to find this molar mass, you needed to use the expression of lowering of vapor pressure. When you use the vapor pressure expression, you put it the values and you calculated the molar mass of the solute from here. You calculated this value and then put it into the boiling point, that expression which we made that equation as 1. Put that value into that and you can calculate the boiling point. Yes, this is how you solve the questions when you are given two different values. Try to make sense of all the things and try to solve the question. Questions are super easy. Okay, I hope it is clear with you. Now let's move forward. Now you have another question. Question is, elevation and boiling point method is used for determination of molecular mass. Okay, it is used for the determination of molecular mass of what? Let's see. Can you solve this question or not? Pause the video and try the question yourself. I hope you tried this question. Now let's solve this question according to me. Okay. See, first and the most important thing is, whenever you're talking about elevation and boiling point, you need a non-volatile solute. Okay. You cannot have a volatile solute. Okay. So it should be a non-volatile solute. Do you have some volatile solute? So this cannot be your answer, this cannot be your answer. You need a non-volatile solute, first thing. And second, my dear students, how did we know that we will calculate only the mass of solute? See, you know that delta TB is equal to KB into molality, right? Delta TB, if we open this expression, this will be KB into given mass of solute upon molar mass of solute upon given mass of solvent upon 1000, because you need to convert it into kg. So molar mass of solvent is not what you can calculate from this expression. You can only calculate the molar mass of your solute, and the solute should be non-volatile. And the other thing is that the solute should also be soluble. Only then you will get a solution, right? Yes, so you need a solution, so it should be soluble. You need a non-volatile solute so that you can use the colligative property expression. So non-volatile and soluble. So non-volatile and soluble, that is option A will be your correct answer. Option A will be your correct answer. So this is how you will solve this particular question. It was very important question because it was asking something which you have to derive out of your knowledge, right? Yes, perfect. I hope it is clear. Let's move forward to the next question. The question is on your screens, my dear student. Let's try. It is a JEE question. Okay, try this question. It is an integer type question as well. And it is asked recently, 2021, my dear students. When 3 grams of a substance X, so this means that you are given the mass of solute X, 3 grams, okay, is dissolved in 100 grams of CCl4. So you are also given the mass of solvent, which is 100 grams. You are given CCl4. So my dear students, I hope you can calculate the molar mass of CCl4. 12 plus 35.5 into 4. Okay, this is how you will calculate the molar mass. Now, it raises the boiling point by 0.60 Kelvin. So this is giving you that how much it is raised. So delta TB is given to be 0.6. Delta TB is given to be 0.60 Kelvin. The molar mass of the substance X is. So you have to calculate the molar mass of your solute. Such a easy question, recently asked, right? Yes. So how can you calculate this? We know that delta TB is equal to KB into molality. Delta TB is given to be 0.60. KB value is given to be 5 Kelvin kg per mole. So 5 into given mass of your solute is 3. Molar mass we have to calculate divided by mass of solvent in kg. So this is 100 grams divided by 1000. So you need not calculate the molar mass also. You were not required to calculate that as well. This is the equation. Solve the equation and you can calculate the molar mass of your solute. You see, such an easy question in JEE. My NEET students, you can solve this question. Right? Yes. So perfect, my dear students. Let's move forward if you're clear with this question. Can we move forward? Yes, let's move forward. Last question of today. Okay, the question says, I'll give you a hint for this question as well. If 1 gram of a non-volatile non-electrolyte solute is dissolved in 100 grams of 2 different solvents. So you have a solute whose mass is 1 gram and you are given mass of solvent A and B. You have 2 solvents, solvent A 100 grams and you have solvent B and its mass is also 100 grams. Okay, perfect. Whose ebullioscopic constants are in the ratio 1:5. Also, the ebullioscopic constant, let us say it is Kb of A. Let us say the ebullioscopic constant Kb of B is this, and it is given that Kb of A by Kb of B is actually equal to 1/5. This is the information you are given. The ratio of the elevation in their boiling points is, you have to calculate this. So I am very clear. I know that I have to use the expression of elevation in boiling point. So let's use that expression. Delta T for A. First we will use for solvent A. Delta TB of A will be equal to Kb of A into molality. Right? Yes. Delta TB of B will be equal to Kb of B into molality. Right? Yes. Molality of A and here molality of B. Right. Now, my dear students, you know that molality is equal to mass of solute upon molar mass of solute upon, I can say moles of solute upon mass of solvent upon 1000. Now just see, my dear students. In question, you are given that 1 gram of a non-volatile solute. The solute was same and the mass of that solute was also used as 1 gram. So the moles of solute in both the solvents A and B will be equal. So I can say that N of solute is same for both. Right? Yes. Now, if you see, you are also given that 100 grams of 2 different solvents. So, mass of solvent is also 100 grams. This means that this mass of solvent is also 100 grams. So, can I say that molality of A is actually equal to molality of B? Yes, because the moles of solute are also same, the mass of solvent is also same. Clear? Yes. Now we can divide the two. 1 divided by 2. So let's divide 1 by 2. You will get delta TB of A upon delta TB of B will be equal to Kb of A upon Kb of B into MA by MB. I know that both the molalities are equal, so we'll cancel them out. So delta TB of A by delta TB of B will be equal to, you were given Kb of A by Kb of B ratio, which was 1:5. So this is equal to 1/5. So what is the ratio of these two? 1:5. So this is your correct answer. You were asked this? Yes, you were asked the ratio only. It is 1:5. Such an easy question, right? Yes, perfect. With this, my dear students, let's end today's session. I hope you were crystal clear with all the concepts. I tried to make you understand every concept with a particular question, and also we tried to solve all the PYQs so that you will gain a little more confidence, right? Yes, I enjoyed this session a lot. I hope you also enjoyed it. Do let me know in the comments, my dear students. Till then, keep studying. We'll meet in the next session. All the very best.